This is the application of Euler's method. We're going to use this to predict the height, velocity, and acceleration of our model rockets, our water rockets, throughout the whole time of a flight. And the reason we're using Euler's method is that the equations that dictate the acceleration of the rocket are pretty complex, and it's much easier to do them with a simulation than it is to solve them mathematically directly. So that's the idea. Let's see how it works. The first idea here is that suppose we have some function of position versus time, just in general. And let's say it's a really complex function, so it's hard to compute the values. But we'll assume that we know the value of this function at some particular time. So at some time we manage to measure the position and the velocity and the acceleration of an object at one particular time. And now we'd like to know how we can use that information to predict what the rest of the curve will look like, as long as we know what sort of laws of physics it has to follow as it proceeds. So we're going to take some amount of time forward from that and call that time t2, and that gives us a position x2 on the curve like this. And we would like to predict that position using what we know about this point right here, the values for this point, and the way that the acceleration changes, or the way that the curve changes, some information about the physics of that curve. The idea here, as I'm showing here, is that if we pretend right at this moment that the velocity suddenly becomes constant, we can predict out into the future using our constant velocity equation. And if we did that, we would say that the position of the object at time t2 would be right here instead of right here where it actually is. And that's because we've made the erroneous assumption that at this moment the velocity becomes constant. So we get a straight line, and the slope of that line is the velocity constant. And so our predicted value just comes from our standard constant velocity equation, x equals x0 plus vt. Here I'm changing the labels because we're starting at t1, x1, starting here, and moving at a velocity v1 for some amount of time, delta t, and that gives us the value of x2 as predicted if the velocity remained constant. But it doesn't, and so because of that you can see that if we use this method to predict where it was at x2, we would have a significant error here. How can we fix this? The simplest way is to make the delta t much smaller. If we make the t much smaller, then t2 is only a little bit of time after t1, and if we presume a constant velocity, now you can see that it comes pretty close to what the red curve is. You can't even see the difference here. So again, we can predict the value of x2 given x1 and v1 and a small delta t. We can get it pretty well. All right, now what happens if we want to keep on going to a time t3, another delta t after t2? If we still use this velocity from point 1, now you can see that error starting to creep in again. It's starting to deviate from the actual curve. So what we'd rather do is predict what is the velocity at time t2, and then use that in the same way we did from t1 to t2, use that to go from t2 to t3. And to do that, we need to predict what the velocity is at time t2. And to do that, we need to use the acceleration at time t1. So at time t1, we're using the constant velocity, to predict where the thing will be at time t2. And then we're using the acceleration at time t1 to predict how fast it will be going at time t2. And when we do that, now we can redraw this constant slope tangent line here and use that to predict the value of x3 right here by just using the velocity of v2 that we got from this, which we got from the acceleration of v1. And that's how this whole process works. All right, let's take a look at how this applies to our rockets. We've decided to call the rocket flight in 3 phases, the thrust phase, the coasting phase, and the falling phase. We've assumed, and our measurements kind of bear this out, that the acceleration during the thrust phase is relatively constant, approximately constant, and you fit a curve to that and you have the data for that. Now let's look at the coast phase, this part right here. At this moment right there on the curve, that's when the water runs out. So at this point, the whole red section here is just the rocket coasting upward to the top of its flight. And it's subject to 2 forces, and the one in particular we're paying attention to here, and the reason why we have to use this method, is that the force of drag is very complex. It doesn't look like a complex formula. It's just a constant, some constant, times the square of the velocity. But when you put that into our F equals ma equation, the F keeps changing because the velocity keeps changing. So the velocity changes with the slowing down of the rocket, and then that changes the force, which then changes the acceleration again. And all of that's very complex to solve directly mathematically, but we can approximate it using Euler's method like we saw before. Here's what we get. We have the acceleration during the coasting phase is the force, total force, divided by the mass. What is the total force? Well, it's the weight of the rocket pulling down, there's the negative sign, and it's the drag force also pushing down on the rocket. Now let's translate that into formulas. The weight is just mg, like we've seen for many months so far, and the drag force, as I just mentioned, is some constant times v squared. And if we divide by m over here, we get a g, and if we divide this by m, we get this. So in the end, the acceleration of the coast phase is just going to be minus g, which it would be even if there was no drag, and then here is the drag. But notice that the v squared also contributes to the acceleration, which then changes the velocity, which then changes the v squared, and so it's this feedback loop, and we're going to see how that works in just a second. And then finally there's the falling phase, and the only difference between the coasting phase going up and the falling phase going down is this sign right here. On the way down, drag is pointed up, and that's because the rocket is going down, and so the air friction goes in the opposite direction. Now let's switch to our actual spreadsheet for working on the rocket simulation itself. Okay, here we are in the Google spreadsheet. You have a copy of this in your Google folder, student Google folder. I'm going to skip over all that part. Here's an equation we just looked at, and go down to the bottom, or in the middle actually here. And this is where you put in data. You're going to enter things in each of these green boxes, the A, B, and C coefficients for the three equations you fit to the video data, the thrust version, the coasting time, and the fall sequence there. And the water gone time is the time when the water ran out, and I've just made up values. These are not your values. You need to put in your values. That's what I'm going to use to assess your results. And then in this green box, you're going to put your student ID number, and when you do, you'll see this mass number change. It'll take the last three digits here and add them onto that 0.4. So this is the mass of the rocket that you'll have, the empty mass without water that you'll be using. And finally, you're going to be calculating a B value, and here's a hint on how to do that, but I'm going to let you think about that and how to get that. Again, that's going to come from this formula right here. And to do that, you need to know the acceleration and the mass and the velocity of a rocket, of your rocket, at some particular moment in time. And you do have that data, and I'll let you figure that out. I'm just going to make up a value here. I think it'll be something on the order of 0.007. Your values will be different depending on what your numbers are here. So now I'm just going to get into the technique for computing these things. This is the part we just talked about, how at a particular time, if we know the height, the velocity, and the acceleration of the rocket, we can then predict what the height, velocity, and acceleration of the rocket will be at a later moment. I'm going to say that from my thing, that the water ran out at 1/10 of a second. So if I scroll down just a little bit here, here we'll see I have the time increments in 1/100ths of a second. So here's right here is where the water will run out. By the way, notice that when I click on this part here, it's defined as the previous value. So here I am at column B and row 107. So it's taking B106, which is this time, and adding to it this value right here, which is C93. Here's C, and here is 93. So it's always adding 100th of a second, and then each one going down is just the same, the previous row plus 100th of a second. And the reason why we have it defined in terms of this number is that in a later part of this assignment, I'll have you change this number and see how it affects your simulation results. So we'll change the delta t and it'll be recalculated automatically for you. But now let's get into creating these formulas for these values right here. First of all, in the thrust phase, which since I said my time was going to be 1/10 of a second, which goes down to row 10 here, step 10, all of these times right here, all of these accelerations are going to be 1/2, they're going to be double the A coefficient of the thrust phase. This A coefficient is 1/2 A, so it's 1/2 the acceleration. So I'm going to click right here and say this value of the acceleration is going to equal 2 times the coefficient of the thrust value there. So that should be 250, and there it is. And now I'm just going to take that and drag it down until I get to 1/10 of a second. And what just happened? Oops. Oh, this is a good example here. I wanted this 250 to refer to this value right here, which is B84. So if I click here, I get 2 times B84. But when I duplicate down by grabbing this corner and pulling down, it'll change this one to B85 and B86, and that's not what I want. I want it to always refer to this number right here, B84. So I have to put a $sign in front of the B and a $sign in front of the 84. And that way, every time I refer to that in this cell, even when I duplicate down, it will always take double the value of this number right here. So I put enter there, and now I'll try it again. And down I go to 1/10. I'll show you what this is here. All right, so now if I scroll down, you can see that everything down to 1/10 of a second is an acceleration of 250. Now I'm ready to start defining row 2 here. This is the x2, and that's the x1 of my previous example on the slides. So the height at time 0.01 is going to equal, so here we go, equal the previous height, the previous x, plus the previous velocity times the amount of time, and the amount of time we're taking is this number right here. So I click on this, but I always want it to point to that 0.01, so I'm going to put the $signs in like that. Boom. And I click it, and nobody's surprised, the predicted next position is 0 because it had a height of 0 and a velocity of 0, so it's not going anywhere just yet. But watch carefully. Now I need to predict what the velocity will be at 1/100th of a second. And that velocity is going to be just the previous velocity plus the previous acceleration, which is this, times the amount of time, and again the amount of time is this time increment, 0.01, but we want to make sure it's always pointing to that 0.01 cell, not anything else when we duplicate. So I put $signs in, and now I see that the new velocity after just 1/100th of a second is going to be 2.5 meters per second. Now I'm going to grab both of these things and pull them down to right here, like that. It recomputes and tells me now, look, the velocity's gone up to 25 meters per second, and the height is 1.125 meters, which doesn't sound very high. So my guess is that some of the values I put in here to just make up this situation are too big or too small. By the way, I'll scroll over here. This is a sort of product of your simulation. It's going to automatically plot the points that you create. You can see here it's already starting to put in the points that I've just changed from 0. So now we have the height of the rocket, the velocity of the rocket at the time when the water runs out, and that's 1/10 of a second. Now we need to go to the more complex formula, and for that we need to figure out what the acceleration is here. And this is going to be the acceleration during the coasting phase. And if you recall, and if you don't recall, I'll just scroll back till we see it. During the coasting phase, it's going to be minus g minus bv squared over m. So let's put that in. So I come back down to here, and I'm going to say the acceleration is now going to equal minus g, so that'll be minus 9.8 minus bv squared. So b is going to be this value. I just made this number up. You'll get a different value, b, but I want to make sure it always points to that particular value, so I'm going to put dollar signs on this C95. That's my b value, times, whoops, what's going on here? What did I do? C95, I'll just type it in up here, times the velocity squared, so I'm going to put this in parentheses. The velocity I'm going to use is the previous velocity. Here it is, right there, the velocity at the previous time. I hope this works out. V squared, up arrow 2. That gives me the BV squared, and now I need to divide that whole thing, this whole thing, and I'm going to put parentheses in just so it's really clear. I'm dividing the BV squared by the mass. And the mass of the rocket is right here. And again, I want to make sure it continually points to that particular cell value. So I put those in. Now I'm ready to go. I hit enter. And it tells me now, all of a sudden, the acceleration is minus 20. Minus 20. Let's see how that compares to what this was. I thought during the coast thing, I just made up this number, minus 7. According to these numbers, it should be, the acceleration should be minus 20. This should be half of that, minus 10. So we're in the right ballpark, but it's not exactly the same. That's okay. So now we've created a formula for the acceleration, and we can drag that down. And I'm just going to bring these down one more row to see what we get here. So now we're up to 27 and this. So now this is the first row that goes with the coast phase right there. It's now coasting. The acceleration is negative, which means it's going to be slowing down. But its current velocity is 27.5. And now I'm going to drag down, and you won't see this until I let go. And I'm just dragging down, I'll just estimate down to about 200. I'll just go a little farther and see what we get. Okay, so I'm just going to let it go here. And I look at the velocity. You can see the velocity is getting smaller and smaller. When it gets to the top, the end of the coast phase, that velocity should be 0. So I'm very close right now. I'll just go a few more rows and check. Nope, still got a little ways to go. A little more. There we go, right there. So right here, it's at the top between these two rows at 2.18 and 2.19 seconds, like that. So at this point, we're at the top. Now, and you can see that the acceleration is just g. Now we want to change the acceleration so that the drag becomes positive. And it's a very simple change. This is at row 219. For me, your rows will be completely different. 219, all I want to do is go up here and change this formula from a minus bv squared to a plus. That's that. Hit enter. You can see it doesn't really change the acceleration much because the velocity is almost 0. Yes, right here. So now I'm going to drag this. Is that what I said at 219? Is this where the plus was? Yes, right there. That's the plus. I'm going to drag this whole thing now and keep going down until the rocket hits the ground. How will we know the rocket hits the ground? And that's when the velocity is 0. So I'll just go this far and see what I get. Not the velocity equals 0, so the height equals 0. The height is still 19, so I have a ways to go. So I will pull down some more. Oh, still 9. All right, let's go. I think this is because my drag value is too big. Oh, now I'm underground. I went too far. Column C is the height. So I'm just looking where the height goes to 0, and that is right here. So this right here, I'll just highlight it here in red. This row right here is where it hits the ground. It's only 10 centimeters above the ground right here. So the whole flight time then, according to this simulation, was 4.66 seconds. It hit the ground with a velocity of negative 18.4 meters per second, and its acceleration at that point was minus 4.058. Okay, that's what we got. So I'm just going to make the rest of it 0. So I'm going to put zeros here because after that it's on the ground. And the reason for that is that I want the plot to come out right. I don't want it to start digging into the ground. So I'm just going to go down to where I had it 0 before. Where did I go? Right there. So I just want everything to be 0. So I'll just let it go. So everything from the red marker on down is 0. And now if I scroll back all the way to the top, or almost all the way, to where that plot was, the graph, hello, there we go. And now if I bring it, whoops, if I bring, oh, come on. If I bring the graph over, why doesn't this, that's it. Okay, so now we can actually see the profile of the flight. It almost looks symmetric. I think when you put in realistic numbers from your data, you'll find that the curve is not symmetric, and you'll see how that goes. And you get that, by the way, by answering questions on the second page. You get to discuss that. And these are the questions on the second tab at the bottom. So be sure to click that after you're done doing the simulation. And that's all there is to it. That's quite a bit, actually.